Hello, this is Professor Keene. We are discussing Proposition 4, Theorem 4 from Newton's Principia. You'll remember in the last lecture, we mentioned that in this proposition, Newton is considering two objects that are moving at uniform speed in circular orbits. These two orbits have different radii. And what I've drawn here is a reminder. So object 1 is moving around an orbit with a radius capital R, and during some time interval delta t, it moves through some arc length. Object 2 is moving around a smaller circle with radius little r, and during the same time interval, it's going to go through a different arc length. And what he's claiming in Proposition 4, Theorem 4, is that, first of all, a centripetal force is required to hold each body in its orbit, and that's what we proved in the last lecture. The second claim that Newton is making is that the centripetal force required to hold object 1 in its orbit is related to the centripetal force required to hold object 2 in its orbit. And the centripetal forces are related by a specific formula, and that is a formula I've drawn in orange. And what I'm going to do in this lecture is go through a proof of this relationship. Okay? So in order to prove this, I'm going to need to draw a few other circles. So I'm going to schematically draw, maybe I'll draw these up here. So I'm going to draw, and actually, tell you what, I am going to cheat and use a toolbar to make a nice circle. Okay, so let's draw, let's get rid of that one. Let me draw one circle, a big circle right here, and a small circle right here. Okay. That'll make my life a little bit easier. And now I'll go back to my regular marker. Okay, so I have those two circles, and let's draw some lines on these circles. You'll see why I'm doing this in a moment. Okay, so let's suppose, first of all, oops, that's not what I want to do. I want to get rid of that. Okay. I'm going to draw the diameter of this circle, and I'm going to label some points. So this will be point A, this will be point B. By the way, while I'm drawing, I'll mention this is meant to be the orbit of this body. This is meant to be the orbit of this body. Okay, I'm going to label the center of this circle S, and I'm going to draw a tangent like this, and then drop it down like this. I'll label these points right here. This will be point E, and this will be point B. I'm drawing all capital letters here, by the way. And this point we will label capital C. And then I'm going to draw a line from here to the center of the circle. And I'm also going to draw a line here to that edge of the circle. Okay, and I'm going to do the same kind of thing over here, except I'm going to use small letters. So this will be a small s, this is a capital S, this will be a small a. I'll draw a tangent once again to a small e, drop down there, call this small b, come over like this, small c. Oh, that's not very straight. Try that again. That's even worse. Try one more time. It's better. Okay, and then let me continue this diameter down here to point. Why do I have 2 point B's? Oops, this was meant to be a point D, so I messed this up. This is point D, by the way. This is point D down here. And then another line. Oh, I'm just having a lot of trouble with that one. That's a horrible line, but that's going to have to suffice. Okay. Now, how am I going to use these diagrams? So here's the argument. As this object, let's suppose this object is starting out at point A. And if it's starting out at point A, if there was no centripetal force acting on the body, then it would end up over here at point E. It would just sort of go in a straight line. So if something was in an orbit and suddenly you turned off the centripetal force, it would go off at a tangent. It would go along to point E. So here's my first point I'd like to make, is that the object that is orbiting would move to point capital E or little e in the case of the second object if there was no centripetal force. If there's no centripetal force. And if we want to be really careful about this, let's give our justification for why we think this. This would be by Newton's first law, or his axiom 1. Axiom 1, or Newton's first law. An object in motion tends to stay in motion in a straight line unless a force acts on it. Okay? That's the first thing I'd like to mention. The second point that I'd like to mention is that, well, when there is a centripetal force, it is going to deflect the object. So if there's a centripetal force acting inward, the centripetal force is going to deflect it inward, and it's going to cause it to move along the arc instead. So the centripetal force deflects the motion by the length of the line segment EB. So this line segment. So whereas it would have ended up over at E, instead it ends up at this point right here, which is deflected by a length EB. So it's deflected by length EB to arrive instead at point B, right? And the point, one additional point that I'd like to make is that the force that's required, the force required to do this is proportional to the length of EB. So in other words, the force that's required, the centripetal force, is proportional to the length of the line segment EB. In other words, if the force was bigger, then the deflection would be bigger. If the force is smaller, the deflection would be smaller. It's proportional to EB. And this is by Newton's axiom 2, or Newton's second law. The change in motion is proportional to the force applied. Okay, so the force is proportional to the motion generated, and it's in the direction of the motion generated. So if there's an inward force, it's going to deflect it in the inward direction. Okay, and it's likewise over here, whereas the object would have arrived at small e, it arrived at small b, and so the force acting on the small one is going to be proportional to the line segment EB, right? So what we can do now is we can say there's a relationship between the force required to deflect the object 1 and the force required to deflect object 2, and the relationship between these forces is the line segments EB to little eb. Okay, now we haven't gotten really very far yet, but that's an important point we're going to need to start from. And moreover, because I've drawn a rectangle here, I'm drawing a line horizontally over here. The length of EB is also equal to the length of AC, and the length of little eb is equal to the length of little ac. So we could equally well write that ratio as AC to AC. Okay, now this is, like I said, a modest progress here. We've related the forces to the lengths of this line segment to this line segment, and eventually we want to be able to prove this right here. So we're going to have to do a lot more work in order to get to that point. So how do we get to this point? And we're going to need to use some geometry. Geometry to prove claim 2. Okay, so let's go ahead and do that. So let me remind you of some properties of circles. So I'm going to go back and draw a circle once again. Go to my toolbar and draw a nice circle. So let me remind you of some properties of circles. Like that. Get rid of that. And get rid of this toolbar. Let me remind you of some properties of circles. So if I draw a diameter across a circle, and I'll call this point A up here, and I call this point D right here, and I put a dot on the circle, and I draw a chord across like that, and then a line going to that, this is a triangle that is inscribed in a circle, and the hypotenuse of this triangle is the diameter of the circle. Okay? And I'm also going to draw a line across like this, a horizontal line with a 90-degree angle. Okay? So this is a little aside here. Let me get rid of these. So this is an aside, a geometrical aside. Okay? So, and let me label this also. B is this point right there, and C is this point right here. Here is the claim. This is just strictly a geometrical claim, is that triangle ABD, this big triangle right here, is similar to triangle ABC, this little triangle right here. This triangle, the big triangle, is similar to the little triangle. How do we know this? Why do we know that? Well, because if you draw a triangle inside, you inscribe a triangle in a circle where the hypotenuse is the diameter, then this angle right here must be a 90-degree angle. So the first point I'd like to make is that angle ABD is equal to 90 degrees. This, by the way, you probably don't remember that. Maybe you do. Maybe you remember this from geometry, but this is by Euclid. So if you look at Euclidean geometry, by Euclid, book 3, point 31, is that when you draw a triangle inside of a circle, it makes a 90-degree angle. It doesn't matter where you draw this triangle. If you drew it like this, as long as the hypotenuse was the diameter, you would get a 90-degree angle right here. Okay, so I'll just take that for granted. Okay, and then secondly, we can see that both this small triangle ABC and the big triangle ABD share this angle right here. So both a triangle ABD and triangle ABC share angle BAD, that angle right there, BAD. Okay. Now notice that since both of those triangles have a 90-degree angle, and since both of these triangles share this angle, that means that this angle here, the third angle, has to be equal as well. So all three angles of triangle ABD and triangle BAD, ABC, triangle ABC are equal. In other words, these two triangles have all the same angles, which is exactly what we mean when we say that they're similar triangles. So this triangle and this big triangle are similar. Now, why is this relevant? Well, because we're going to need to use this in order to make this relationship into this relationship here. Okay? So let's continue with our proof then. And by the way, I forgot to draw a couple of lines here. I'm going to draw another line here and another line here. That's going to be relevant. It's going to play the part of this line right there. Okay. So point 1, point 2. Now let's go back. Let's pick up our discussion at point 3. Okay, so this all over here was an aside, just because that's going to be relevant for our argument. Okay. Now, the next point I'd like to make regarding this situation here is that line segment AC is to arc AB in the same ratio as arc AB is to line segment AD. Why is this true? Well, this works as long as this arc length AB, if this is a small arc length, it can be approximated by this chord. So for small arc length, for small arcs, the arc length AB is approximately equal to the line segment AB. So what we're going to do essentially is say that AC, if we can show that AC is to AB line segment as AB, that line segment, is to AD, then we will get this right here as long as this is a very small arc. So we're considering very small time intervals, put it that way. So is AC to AB equal to AB to AD? In other words, is this length here to this length here in the same ratio as this length here is to this length here? We're relating those. How do we know that's true? Well, now we just go back to this triangle I just demonstrated. Since ABC is similar to ABD, those two triangles, that implies immediately that the short length of this little triangle is to the hypotenuse in the same ratio as the short length of the big triangle is to the hypotenuse of the big triangle, which is exactly this relationship here. So that means that this is in fact true, that AC is to AB as AB is to AD, because those, after all, are similar triangles, and that means that AC is to the arc length AB as the arc length AB is to AD. So I would just say this is approximately true as long as we're talking about small delta t's, small displacements like that. Okay, there we go. Now, point 4. Well, AC, that line segment, then we can rearrange this right here, or alternatively rearrange this. We'll solve for AC. So AC is equal to the arc length AB squared over AD. So here we're just rearranging our point 3. So there's just algebra right here, really, using that. And likewise, by the way, when we're working with this big circle, we can also work with the little circle and say little AC is equal to little AB arc length over little AD, right? So that's the same thing whether we do it on the big circle or the little circle. Okay. Point 5, I hope you're following along here. Now, let's go back to this point right here, point 2. We said that when we relate these centripetal forces, they're in the ratio of big AC to little AC. Well, we have expressions now for big AC and little AC, so let's go ahead and plug these in. So that is big AB arc length squared over line segment AD. And here we have little AB arc length squared over little AD. You're starting to see probably it's starting to look more and more like this, right? Okay, and now notice that AD right here is the diameter of this circle, and AD is the diameter of this circle. Okay, so and also notice that AD appears here and AD appears there. There's going to be a ratio of those, and the ratio of these diameters is going to be the same as the ratio of the radii, AS and AS. So we could just replace the diameter ratio with the radius ratio, which would then leave us with AB arc length squared over line segment AS. So I'm replacing, all I'm doing here is I'm replacing the diameters with the radii, right? And now look what we have. we have AB as the arc length for the big one, so I'm just going to replace that with the arc length squared, and AS with the radius of the big circle. And this AB is the arc length of the little circle squared over the radius of little circle, and voila, we have exactly what Newton was trying to argue for. Okay, so let me just summarize what we've done here. There's been a lot of work to try to do this geometrical and mathematical proof, but the main point here is that if we have two objects that are going in orbits around a circle, and they're both going at a constant speed, although perhaps a different speed than the other one, and the two circles have different radii, what we've done is shown that there's a force required to hold each of those in orbit, and that the forces required to hold them in an orbit have a particular mathematical relationship. And the mathematical relationship is given by the formula that is in orange. So if we know in a particular interval of time, let's say 1 millisecond, the arc through which one of them moves and the radius of that orbit, and we know the arc through which the second object moves in the same time interval, like a millisecond, and the radius of the second circle, then we can deduce what the ratio of the forces that are required to hold them in orbit are. Why is this important? Well, as I mentioned before, Newton is going to use precisely this proposition to determine the strength of the gravitational force required to hold, for example, Jupiter in orbit around the Sun, and Saturn and Mars, and for that matter, the Earth in orbit around the Sun. So I'm going to stop there, and I'll pick up this discussion next time.